Hello everyone, my name is Chris Lu from Sun University. I'm going to lead today's practice session. In previous session, we have learned how to develop carbon balance equation from carbon flow diagram and how to create matrix equation from carbon balance equation. In today's practice session, we're going to learn how to calculate diagnostic variables from a carbon cycle compartment model. These diagnostic variables are based on the matrix representation and the traceability analysis framework. We will start from working mathematically on the matrix equation, and we will recognize the traceable component from the equation. Then we will use the TICO model in Python script as an example. We can play with the model to see how the carbon storage capacity are going to lead the change of the carbon storage. We will understand how the traceable component can help explain model performance. We'll also tune the parameter to see how traceable component and the carbon storage are changed accordingly. The development of a land carbon cycle model diagnostics is to meet the increasing need to understand land carbon cycle prediction. Land carbon cycle models have been more frequently used recently to estimate land atmosphere carbon feedback. However, scientists are facing big challenges that land carbon cycle models provide quite divergent predictions. For example, land carbon uptake. Model intercomparison projects have been developed. They put lots of effort to understanding the differences among models. For example, differences in model structure, parameters, initial value, and forcing have been widely discussed. There are still two big challenges. First, even if we identify above differences among models, how to quantitatively evaluate their contribution to carbon cycle? Second, can we understand these differences with scientific meaning? Here is an example how models simulate differently in soil carbon. This is a spatial comparison in soil carbon density between simplified models and HWSD dataset. The prediction are actually very poor and can be seen from all models. How should we understand these model differences and bias? Understanding the model performance is usually like giving a medical examination. We make examination to identify which part of a body is sick. Land carbon cycle model diagnostics can be even more sophisticated. The different carbon storage simulated by different models could be due to differences in multiple processes such as photosynthesis, plant respiration, soil decomposition, litterfall, and many other processes. Most of these processes are also related to environmental conditions, such as the rainfall and temperature. But what the model can tell us is only how carbon storage is simulated. We need more detailed diagnostics from the models. This is the motivation to develop traceability analysis framework. This picture is a blind man touching elephant story. Someone says it's a snake when he touches the elephant nose. Someone says it's a tree when he touches the elephant legs. If they talk to each other, they probably can assemble the elephant together. The traceability analysis with the matrix representation does a similar work to understand each traceable component first, and then assemble them together to understand the carbon storage. But first of all, the traceability analysis framework had to make sure that the carbon storage can be exactly reproduced by the traceable components, which means the assembled creature should look like an elephant. Practically, we do reproduce the carbon storage since the relation between the carbon storage and the traceable components are fully expressed by the mathematical matrix equation. In this way, contributions of a traceable component can be also calculated. In addition, these traceable components, such as the residence time, are usually with scientific meanings. The comparison of such traceable component with observation is also possible. Here we are going to review and practice how to calculate carbon storage capacity, potential, and the residence time. Most land carbon cycle model can be formulated in equation 1. This is a carbon balance equation in matrix format. Change in carbon storage can be expressed by carbon input and carbon network transfer. If we can find an intermediate term, in this case we find the AKC, and we put the intermediate term on both sides of equation 1, we are able to formulate the dynamic of carbon storage in equation 4. If you have read each paper, you will know that in this equation 4, this first term is the carbon storage capacity and the second term is the carbon storage potential. The carbon storage capacity can be further decomposed into residence time times the carbon input. The critical step is to find an intermediate term. However, different models may formulate differently in the intermediate term. We are going to practice formulating above traceable components with two examples. First, we are going to write down the equation 4 for the take-home matrix model, and second is an optional task. If you are capable, we are going to write down the equation 4 for the COM4 vegetation model. First, we are going to practice writing down the last slide's equation 4 for take-home model. Because this is just a simple version of a TICO, and the soil decomposition isn't related to environment. So there's no environment scalar in this carbon transfer term. Our first assignment is to write down the intermediate term from equation 1. Then, after finishing the intermediate term, we are going to write down the full equation. Then identify the carbon storage capacity, carbon storage potential, and the carbon residence time from this equation. Please pause until you finish, because you will find the answer in the next slide. Here is the answer of the first task. The intermediate term is expressed by the transfer coefficient matrix times the decomposition rate matrix K. The full carbon dynamics equation is expressed in equation 4. The carbon storage capacity, carbon storage potential, carbon storage resistance, and the carbon input are in different colors. So please check if you have made them correct. The second task is an optional task. You may skip this one if you feel too difficult to handle the mathematical equation. In this task, we are going to practice working on a more complicated model, COM5, vegetation carbon nitrogen cycle model. This is the flow diagram of the model. Vegetation carbon state variable includes leaf, vine root, leaf stem, dead stem, leaf cost root, and dead cost root. Each of these pools have two corresponding storage pools, short-term and long-term storage of non-structural carbohydrates. The COM5 matrix representation considers totally 18 carbon compartments. The dynamics of these compartments are controlled by photosynthesis, allocation, phenology, metallicity, and fire together. So the carbon transfer term can be simply written into one AKX term anymore. Three AKX terms representing different processes have to be added together. If the matrix carbon balance equation is formulated with the three AKX terms, can we still reorganize it to find those traceable components? Can we find an intermediate term and write down the new carbon dynamic equation, the equation 4 in the 5th slide? Then you are required to identify the carbon storage capacity, carbon storage potential, carbon residence time, and carbon input from the new equation. Please pause the video before you go to the next slide to see the answer. This is the answer of task 1A. The intermediate terms become the sum of the three terms. This table summarizes all parameters we need to tune. Finish your simulations and analyze your results. Fill those blanks and compare the diagnostics among different simulations. Please pause the video until you finish. Now let's practice running TICO on the cobble tree. First, let's open Train and select Unit 3, Exercise 3, and the default case. Then click the Set Output folder to tell Train where to create a case directory. This step should be done before running the model or before opening source code, because Train needs a place to save the results or duplicate a source code for each case. Then click Open Source Code and read line 10 to 44 to get familiar with the configuration and model parameters. For example, on line 40, end year tells the model to run 10,000 years. Now, let's get familiar with the parameters. All the parameters are in the source code from line 10 to 44. For examples, U in above equation represents carbon input. The corresponding parameter in the code is input underscore fluxes in line 38. Now let's find the corresponding parameter for the rest of those traceable components in the code. The answer will be on the next slide. Here are the line number of those traceable components in the code. Now we are ready to click Run Exercise. Running the model will usually take several seconds. A window with a finished will be popped up once the task is successfully run. Results and figures will be automatically generated in the case folder. The output file, the Excel file, contains annual results in carbon input, 7 carbon pools, and the diagnostic outputs. The diagnostic outputs include the residence time, total equivalent carbon storage capacity, and the carbon storage potential. Graphic and the result summary will be in results.png, since carbon input and turnover rates are all constant. The carbon storage capacity is time independent in this case. The summary in the figure tells us how much is the steady state carbon storage, how much are these traceable components at steady state. Let's answer following two questions. First, does the carbon storage always change towards the carbon storage capacity? Second, how does the carbon storage potential change? This is second task in exercise 3. Let's try different initial values to see whether carbon storage will ultimately converge to the same carbon storage capacity. Change the default case to change initial pool size 1. By clicking Open Source Code, let's edit the source code on line 44. Replace the initial value with the number we provided in the slide. Then click Run Exercise and check results. Then let's change the case to change initial pool size 2. And repeat previous steps. Replace the initial value with the lower values as we provided. Then click Run Exercise and check results. By comparing these two simulations, we can see carbon storage from two initial values stabilize at around 35,000 gram carbon per meter square, which are similar to the carbon storage capacity. Now we are able to answer these questions. Especially, can we think about whether carbon storage capacity depends on the initial value? Let's fill the blank for exercise 3.2 in slide 11. This is the third task in exercise 3. Let's try different carbon inputs. Change the case to change carbon input 1. By clicking the open source code, let's edit the source code on line 38. Replace the carbon input value with the number we provided on the slide. Then click Run Exercise and check results. Then let's change the case to change carbon input 2 and repeat previous steps. Replace the initial value with the higher value as we provided. Then click Run Exercise and check results. By comparing these simulations, we can see carbon storage stabilizing at different carbon storage capacity. Now let's answer this question. Especially, can we think about whether carbon storage capacity depends on carbon input? Let's fill the blank for exercise 3.3 in slide 11. Let's summarize the simulation in exercise 3. Different initial values don't result in different capacity and residence time. Different carbon input result in different carbon storage capacity, but not residence time. Carbon storage always changes towards the carbon storage capacity in all these cases. In exercise 4, we are going to learn how parameter will impact the carbon storage capacity through carbon input and the residence time. We know carbon storage always chases carbon storage capacity. This exercise will also help us understand how parameters determine the carbon storage at steady state. Let's finish this task one by one and fill the blank. This is the first task in exercise 4. Let's try different turnover rates. Select Unit 3, exercise 4, and the case low foliage turnover rate. By clicking Open Source Code, let's edit the source code on line 26. Replace the turnover rates with the number we provided in the slide. Then click Run Exercise and check results. Then let's select case low passive soil turnover and repeat previous steps. Replace the turnover rate with the lower value as we provided. Then click Run Exercise and check results. Here are results from two different turnover rates. By comparing these two simulations, we can see carbon storage simulated stabilize differently. Can we think about how turnover rates impact carbon input or residence time, and therefore the carbon storage capacity? Let's fill the blank for exercise 4.1 in slide 25. This is the second task in exercise 4. Let's try different allocation fractions. Select the case high allocation to foliage. By clicking Open Source Code, let's edit the source code at line 10. Replace the allocation fraction with the number we provided in the slides. Then click Run Exercise and check results. Then let's select the case high allocation to wood and repeat previous steps. Replace the allocation fraction with a higher value to wood as we provided. Then click Run Exercise and check results. Here are results from two different allocation fractions. By comparing these two simulations, we can see carbon storage stabilize at different carbon storage capacity. Can you think about how allocation fractions impact carbon input or residence time, and therefore the carbon storage capacity? Let's fill the blank for exercise 4.2 in slide 25. This is the third task in exercise 4. Let's try multiple change together. Select the case multiple change 1. By clicking Open Source Code, let's edit the source code at line 26 and 38. Replace the input and turnover rates with the number we provided in the slides. Then click Run Exercise and check results. Then let's select the case multiple change 2 and repeat previous steps. Replace the input and turnover rates with a higher value as we provided. Then click Run Exercise and check results. Here are results from two different carbon input and turnover rates. By comparing these two simulations, we can see carbon storage simulated at different carbon storage capacity. Can you think about how input and turnover rates impact the carbon storage capacity? Let's fill the blank for exercise 4.3 in slide 25. Let's summarize the simulation in exercise 4. Here are the answers to slide 25. Let's think about how residence time and carbon input impact the carbon storage capacity. How different parameters impact the residence time.